Welcome to NASA's Jet Propulsion Laboratory in Pasadena, California, and welcome back for now the post-landing briefing for the Phoenix mission to Mars. If you were with us earlier today, we said that it would be an exciting evening tonight, and I don't think any of us knew exactly how exciting it was going to be. And we want to show the team members a little bit of that excitement because, of course, they were part of it, but they haven't seen how it looked to everyone else. So we're going to begin looking back a few hours ago, what it was like in Mission Control as we heard Phoenix all the way descending to the surface of Mars.
Atmospheric entry on my mark. 5, 4, 3, 2, 1, mark.
We have now entered the atmosphere and are starting to slow down.
Phoenix now 1 minute past the entry point. We still have a signal by Odyssey. At this point in time, Phoenix goes normally through peak heating. At this time, we still see a signal by Odyssey. Standing by for Odyssey switch to 32K in 45 seconds. Stop of Odyssey canister data and switch to 32K in 10 seconds. Odyssey switch to 32K detected. We have Odyssey locked up onto Phoenix carrier. Standing by for expected parachute deployment and Phoenix switch to 32K. At this point in time, Phoenix would have normally deployed its parachute, standing by for telemetry acquisition. Phoenix switch to 32K detected. We have data lockup, parachute deployment trigger detected, heat shield trigger detected, ground relative velocity 90 meters per second. Ground relative velocity 80 meters per second. At this point in time, standing by for radar RF on and altitude convergence. Radar switch to altitude mode. Standing by for altitude convergence. Land leg deployment trigger detected. Ground relative velocity 60 meters per second. Standing by for altitude convergence. Radar reliable. Altitude 2,000 meters. Altitude convergence detected. Altitude 1,800 meters, 1,700 meters, 1,600 meters. Standing by for lander separation. Altitude 1,100 meters. Signal may drop out during lander separation. Altitude 1,000 meters. The separation detected. We have reacquired the signal. Gravity turn detected. Altitude 600 meters, 500 meters. 400 meters, 250 meters, 150 meters, 100 meters, 80 meters, 50 meters. Constant velocity phase detected. Altitude 40 meters, 30 meters, 27 meters, 20 meters, 50 meters. Standing by for touchdown. Touchdown signal detected. Landing it sequence initiated. Helium vent detected. Standing by for normal termination of EDL comm.
All right. We have a few of those mission team members to the mission support area back there in the back, including Richard Kornfeld, who got to count us down there all the way to the surface. Okay, now we're going to go up to our panelists, and I want to introduce all of them to you. Of course, joining us today, we have NASA Administrator Mike Griffin. Ed Weiler, NASA's Associate Administrator for the Science Mission Directorate. Charles Alachi, the Director of the Jet Propulsion Laboratory. Peter Smith, you all know by now, but he's the principal investigator for the Phoenix mission from the University of Arizona in Tucson. Barry Goldstein, the Phoenix Project Manager from JPL. And Ed Sedevy, the Project Manager from Lockheed Martin Space Systems in Denver. We're going to begin with comments from the administrator.
Thanks very much. I was thinking about what I was going to say tonight, and for some reason, maybe the presence of our various congressmen and elected representatives in the audience cued me in on this, but I was thinking back to a very long time ago, preparing for my first congressional testimony ever. I had all my hair then, and it was black. And I was looking for advice on how to handle it from an older friend who said, well, remember that an expert is a person whose head is full and his hands are empty. He said, experts make it look easy. So don't carry in a whole lot of stuff. And I've tried to follow that rule ever since then, but what stuck with me was experts make it look easy. Well, today you had a chance to watch a team in action making something that is incredibly hard to do look easy. And you know that they are the most expert of the expert when they can do that. I'll just give you one measure of that expertise. Accuracy at entry interface had to be well inside 20 kilometers of error after a 650 kilometer, million kilometer round numbers trip from Earth to Mars, and yet had to be delivered to something like 20 kilometers of accuracy on entering the Martian atmosphere. That's something like fewer than 1 part in 10 million of accuracy. Very few things that human beings do in any walk of life are as precise and accurate as 1 part in 10 million. And that's the kind of accuracy and precision with which navigation is done here at JPL at one of the technical pinnacles of the space business. There will be many more measures of the kind of expertise that have to be applied to pull off what you saw here today, but I won't bore you with them. It's not, I don't want to take up too much time. I want to let these people talk to you about what they've been able to do, but I want you to think about that 1 part in 10 million of accuracy and precision that these folks delivered in order to be able to land the spacecraft on Mars, and think about that. Thanks very much.
Thanks, Mike. One thing I wanted to do was recognize all the people that make up this team, especially some international groups which you may not be aware of. Of course, we have the PI and the head of the science team, Peter from University of Arizona. Our prime contractor was Lockheed Martin Space Systems. Of course, JPL had some role in this, right, Charles? But we also had a major collaboration with the Canadian Space Agency, and I believe the president of the Space Agency, Guy Bujold, is here today. They provided the meteorology system, the system that will study weather on Mars. And even another European country, Germany, was involved. The Max Planck Institute actually provided the robotic arm camera. I, too, don't want to take up too much time because I'm sure you want to hear about the science and the engineering that went into this landing, but let me tee off on something that Mike was talking about. There's a question somebody asked me earlier today, because I've been accused of being perhaps too cautionary by saying this wasn't a trip to Grandma's house, and these guys made it look so easy. And I'll admit they made it look easy, but let me remind you the math. Before tonight, 55% of all landing attempts on Mars have failed. After tonight, 50% have failed. If you consider that routine, that's your choice. Now, it did look routine because, as Mike said, you had an incredible team, working incredible feats. I did give some thought to this 440 million, 660 kilometer, 1 part in 10 million. If I did my math right, and I apologize to those reporters, I told you it was a termite in Australia. It's actually the following. Doing something to that accuracy, and Michael appreciate this as a golfer, it's like trying to hit a hole-in-one, but you tee off in Washington, and you hit the ball 10,000 miles, and you score a hole-in-one in Sydney, Australia. That's 1 part in 10 million. 4-inch hole. That's not a bad shot. So, Charles, not a bad shot.
You have to remember that hole is moving. I'm sure Mike would appreciate. Not to say that Australia is moving, it's just Mars is moving.
So, with that thought in mind, maybe it is more like hitting a termite in Australia.
No, I think, I'm sure you know that throughout history, exploration always required courageous people and people who have superhuman dedication. And it's courageous people who undertook the exploration tonight and got Phoenix, on the surface of Mars. Many people thought that this will not be possible, that we will not be able to succeed. All of us knew this is very risky, mission. But tonight, this team made history. And they will be remembered forever that they are the first people who explored the polar region, of Mars. And there is no telling what discoveries we'll be seeing over the next, 90 days. As Ed said, it's a team which brought the best, or some of the best, from all of NASA. Every center of NASA participated, in this endeavor, be it in the launch, or be it in the heat shield, or being in the trajectory. So it really was a NASA team effort. Both the human program and the robotic program worked together. We had some of the best from academia, as exemplified by the University of Arizona and Peter, and the best of industry, as exemplified by Lockheed Martin. So one thing I want to ask you, next time it's clear, and you go outside and you look at Mars, just think that our nation had 3 stations on that planet: Spirit, Opportunity, and the Order of the Phoenix, just to make the Harry Potter people feel good. So with this, I'll turn it now to Peter.
Thank you, Charles. Well, after that awesome landing, and I'm going to let Barry and Ed talk about how they did it. They are really responsible. I had to wait for an entire hour and a half for that Odyssey spacecraft to come around overhead again to see if we had any pictures. And by God, I've been getting some pressure from some of the members in the press that if I didn't get pictures down here, there was going to be a riot. So I won't mention any names, but the Irish press was particularly... So it is my great pleasure and joy to be able to show you some pictures of the landscape around our lander. I have to say, though, we're still looking for Grandma's house. We haven't found it yet, but it's there somewhere, I'm sure. Can I have the first slide, please? And well, this is going to set the stage as to where the pictures are. So that's an image that was done several days ago and shows what we thought might be on the surface. And I have to admit, I haven't seen this yet. There we go. There's the actual mosaic that comes from 4 images stitched together. We had hoped to get a couple more, but I think we ran out of time. When Odyssey came over, we set up what we had, and this was it. Now, let's look at them individually. The next slide. I think you've probably seen these come down over the web. This is that polygonal terrain that we were talking about in previous press conferences. This is what we see from orbit. This is where we wanted to land. We see some small rocks. We see the polygons stretching out into the distance. I know it looks a little like a parking lot, but that's a safe place to land, by gosh, and there's not any big rocks. I think we really nailed it, Charles. That was the place we were looking for, and that's what we've found. Now, that makes it exactly the place we want to be, because underneath this surface, I guarantee you, is ice. There's ice under this surface. It doesn't look like, you don't see any ice, but it's down there. Let's look at another picture. Now we're going to get a little closer, and you can see lots of pebbles and obviously soil and all this, these troughs that you see between the polygon boundaries. Those polygons are probably about 15 feet across. That's what we estimated from the orbital pictures. The next shot, looking down even closer, this one's really quite interesting, and I think you've all seen this, but let's see. This is probably the cutest polygon that I have ever seen. Right, Vicki? I think it's the cutest one. And now the next slide, let's put it into color. Now maybe you haven't seen the color yet. And so the color stretching out to the horizon shows those same three images put together. And now we can zoom into the closer one in full color now. And we can see there are differences in color in the soil. If you look in the upper left of that image, it's a little bit of a darker streak. So this is still not as close to the lander as where our arm can reach. It's still outside of that digging area. So we have not yet seen what we're going to be digging into, but it's probably very similar because as far as you can see, it looks very similar. Now, is it going to be the same as we look all the way around? Who can say? Nobody knows. And it may be that there's something quite different as we look around behind us. So over the next few days, we'll be getting the whole scene filled in. We've only looked at one little sliver of the Martian surface, but it's exactly what we wanted, and I couldn't be more pleased. This is a scientist's dream right here on this landing site. And to tell us how we got there and show us more of the wonderful accomplishments of the landing team and the Phoenix team is Barry Goldstein. Our, yeah, I remember you. I'm a little tired. Excuse me.
Just checking.
Barry Goldstein.
Aren't you guys getting tired of looking at us for these last 4 days? No. Actually, I think you should be. And we've got not only on this side, but in this aisle and this aisle. I'd like the guys on the team. And by the way, I want to emphasize these are just a portion of the team. This is the team members from here at JPL. Can you guys stand up? The accomplishments are for these guys. Incredible job. Just incredible job. I think somebody told me that I look tense tonight. Did somebody say I look tense? No,
You look tense, Barry.
I look tense, but I want to add to the team member theme here. This is just a portion of the team. Obviously, you know we have a huge team with some of the best engineers in the world at Lockheed Martin working on this project. But there are, obviously, you know about the team at the University of Arizona, but we have so many other participants in this project, and I just want to rattle off a few because we owe a huge debt of gratitude, obviously. The Langley Research Center, they were responsible for all of our aerodynamic work, aerothermal work and aerodynamic work. They were exceptional on this. Dryden, the Dryden Center, we did a number of tests out in the desert to make sure that radar that we had to get that one signal on, just incredible. Ames Research Center, we had people at the Ames Research Center test our heat shield, all of our heat absorbing materials, also working on some of our ground software. I want to say a special thanks to MRO and to Odyssey. Odyssey in particular. Odyssey, you've been out there waiting 8 years to the spaceship, and it finally happened today, so here we are. DSN, exceptional performance by the DSN. Goldstone, Canberra, Madrid, you all performed for us. We owe you everything. You were just wonderful. Some more international partners, Charles, that we shouldn't leave out. The University of Copenhagen, they've provided us the telltale. We'll get some wind measurements coming up pretty soon. The University of Neuchâtel in Switzerland, who've provided us our atomic force microscope. Pretty soon we'll see things finer than finer than a human hair, or 1/10 or 1/100th, Peter, is that right? Have a human hair with the atomic force microscope. And the Finnish Meteorological Institute in Finland has provided us a pressure sensor. So this is a huge collaboration, and there are hundreds of others, so forgive me for who I have left out here. This has just been an incredible partnership. Anyway, let's see, I guess you want to hear a little bit about the landing. Can I have the first slide, please? Okay, it took a lot of ribbing for this today. The infamous blue ellipse that I've spent a couple of press conferences here talking about was basically our 99% probability landing ellipse. What the team has done, and you heard how wonderfully ADL Communications worked, we have taken all of the IMU, all the gyro data as we descended through the atmosphere and propagated our way down from the entry point in the Mars atmosphere and basically calculated with some uncertainty where we actually landed. And the best data we have right now, you see a red circle on the right-hand side of this image, 99% probability is we're within that circle. And what has happened, and I believe has happened already, Brian, is those coordinates, or at least dead center of those coordinates, actually a little further south, I think they've adjusted a little further south, have been provided to the Mars Reconnaissance Orbiter team. And in approximately, I would guess it's about 8 hours from now, thereabouts, there's going to be a pass over that area, and hopefully we're going to get an attempt. Well, we definitely will get an attempt. Hopefully we'll be able to image this lander on the surface of Mars. If we miss it that time, 12 hours later, we'll give it another shot. If we miss it again, and keep in mind the incredible accuracy of the HiRISE imager is what makes it so difficult to spot where we are. If we miss it again over the course of the next couple of days, we'll be able to triangulate and really pinpoint where this vehicle is, and we'll get that image for you as soon as we can. Well, let's go to the next image, please. Please. I think I mentioned this a couple of days ago. It was fun for us to show you this image as how we rehearsed it on a simulated deck, but here it is. This is that one image that I mentioned earlier that confirms 3 of the post-landing deployments that we had to do after touchdown. You can see in the middle of the image what looks like an elbow joint. That's because it is an elbow joint. That's the elbow of the robotic arm. But the thing we were looking for is just to the left, which is the open biobarrier, that protective cocoon that we had put the arm in before we had sterilized it, before it was mounted to the spacecraft and then made its way to Mars. And it's getting ready for its deployment. Earliest that'll happen is on Tuesday, but we're going to keep monitoring the temperature for that. So we have confirmation that the biobarrier deployed. You can also see at the upper left-hand corner of the picture is the tip of the meteorological mast, or excuse me, the base of the meteorological mast. Unfortunately, we can't see the mast itself, but we know that the mast is up there because it's not lying next to the robotic arm, which we can see is open. So between those 2 images and the fact that that image was taken by the surface stereo imager, and we know from the right angle, we have confirmed with one picture 3 of the major deployments for this mission. And this is just exceptional. And we had a couple of other kind of important deployments there. Oh, I guess I have landing leg images. Let's show these really quickly. Can I have the next 2 pictures right in a row? 1, 2, that's a left eye and a right eye image of the landing legs. I guess what's most interesting in there is what's missing, which is we didn't really obliterate the surface with the thrusters, which is, I guess, fascinating and good at the same time. So that's really good news. All the data shows we came down with almost 0 vertical velocity. We were at about, what was the number, about 0.1 meter per second in horizontal velocity. Obviously, we were coming down at our planned 5 miles per hour at 2.4 meters per second. That was all programmed, so everything just worked like a charm. This was just wonderful. And with that, let me turn it over to Ed to give you more details about this wonderful spacecraft that's now going to be doing some great science over the next 90-plus sols.
Yeah, and maybe beyond. Thanks, Barry. Before we get into the particulars of the spacecraft status and the performance during EDL, I want to continue on with the theme that Mike Griffin started. And I'm a baseball fan, so I'm going to use a baseball analogy. The JPL nav team was just outstanding, and led by Brian Portok over there. Brian and the JPL nav team fed the spacecraft a fastball right down the middle of the plate, and the spacecraft turned on it and cranked it out of the park. All right? All right, so we were dead solid all the way down. We're a little bit farther downrange than we were expecting, and there's a number of reasons for that, and the EDL reconstruction team will tell us exactly why that happened. When we look at all the parameters that we have from the performance of the system during EDL, it went better than any of the tests and simulations we had run. And the team in Denver is just totally stoked. I was on the phone few minutes before we came in here, and the flight team in Denver realizes that they have a perfectly functioning spacecraft on the surface of the planet, and they're busy trying to understand all the particulars in the data, and they're enjoying the moment right now, and they really do deserve to enjoy the moment. I want to recognize some of the contributors that we have within the spacecraft team, some of our partners, and before I get on with the specifics. The landing radar is absolutely critical. We started with an F-16 radar and figured, well, we'll space rate it. You know, what could be difficult about that? We'll just swap out some parts and oh my gosh. So Honeywell builds the F-16 radar, and the team up in Minneapolis was very patient with us as we drug them through over and over and over again, finer and finer levels of detail of understanding the behavior of the radar and the subtleties of the system interactions, and it performed really, really well. I was a little bit nervous when I was hearing Richard Kornfeld reading off the status, because it seemed like I was waiting forever to get altitude lock. When I talked to the guys back in Denver, they told me, no, it was within 100 meters or so where we predicted. So the radar locked on just as planned. The solar arrays that you're going to see pictures of, the development on those started in 1998, when under the Mars Surveyor 01 lander, and so that's part of my heritage of this mission. I've been working on this lander for 11 years now, with a hiatus in the middle after Ed Weiler shut us down. but
Selected you.
yeah, that's right. But I told him earlier tonight he did the right thing by shutting us down in 2000, although that was rather frustrating at the time. So the solar arrays, now you'll see some pictures of them. They're deployed just as we had hoped. ATK in Goleta, California has been our partner on those. And those of you who follow the space business have seen the pictures of their arrays in the Orion spacecraft. So Phoenix and the success of the landed solar arrays on Mars has significance for the manned program in a big way as well. So there's a lot of very happy people all over the country to see the solar arrays deployed on Mars. The batteries that we're going to rely on to give us heater power all night are courtesy of Yardney in Pawcatuck, Connecticut. And we started that development back in 1998 as well. And those ended up getting their first usage on the MER rovers, and then we picked up from there, and so we're flying the Yardney batteries. And then the last one I want to recognize is Galileo Ivanica, who built the star trackers for us. Those are very complicated subsystems, and those guys have just been phenomenal to work with. And that gave us the attitude that we needed all the way through cruise. They locked on at the first opportunity after Launch Vehicle SEP, and they've been that way ever since. So we've had up and down, left and right, everything that's contributed to the spacecraft has just been outstanding. There's been terrific commitment by everybody involved. Okay, so let's talk about how we did in EDL. Chute deploy, parachute deploy was about 6.5 seconds later than we expected, and that's represented in the fact that we're downrange from where we had anticipated. And then everything else kind of tracks from there. Lander separation was maybe about 5 minutes behind nominal, and then 5 seconds. That would have been a problem. And touchdown was about 7 seconds behind the nominal timeline. The state at touchdown was 5 miles per hour as per scripted with constant velocity mode, and then the horizontal velocity was 0.15 meters per second, which is about a quarter mile an hour. So to put that in perspective, if you're casually strolling around, that's at about 2 miles an hour. That's about 30 minutes an hour, a mile walking. So we came down with the horizontal velocity about 1/8 the rate of a casual stroll in the park. And to do that on the surface of Mars, because that's where a lot of risk of touchdown is if you come in with a horizontal velocity, if there were rocks down there, if there was the polygonal terrain, feature. If you had hooked landing pad in there, bad things could have happened. So knowing that out was really very important. I'll talk about a couple radar parameters, and then we'll go look at some pictures of the solar arrays. We got altitude convergence at 2,188 meters above the surface, and about 2,200 is what we were expecting, so that was pretty darn close. And then we got a velocity lock at 1,549 meters. Those are the two things we needed. With that snapshot, even if we lost the radar at that point, we were probably just fine, because the IMUs could have propagated the state to the surface for us. We completed backshell separation at 962 meters above the surface, and then that's when things got really interesting. That was the part when the free flyer kicks in, and we did the tip-up maneuver at 927 meters, and that was really, really important, because that's where the control system is able to get the vehicle aligned, the center of mass of the vehicle with the velocity vector, and that's how you get maximum control from your control system. We got onto the gravity turn at 769 meters. That's where we turn around, make sure that we're nadir pointing. And then the all-important thing is constant velocity mode. We had an objective of 40 meters, and we got to that point at 54 meters. And at that point, when I heard Richard call out, we're constant velocity mode confirmed, I knew we had it. Because at that point, all we had to do was let it come down to the surface. So it was, we did it, and we did it with style, is the way I look at it. So let's look at some solar array pictures. I think there's an animation first to show the context of these pictures. If we can roll the animation. So obviously we're looking at the spacecraft from the top down, and we'll move in here. We'll take a look at the SSI, which is up on the deployment mast, and then down at the solar array, and there you see the image superimposed on what we got on the surface of Mars. And I'll point a couple things out for you here. On the monitor I'm looking at, it's not all that easy to tell, but you can see reflection on all of the cover glass of those solar cells. And what that means is there's no dust on the solar array, none. And that's terrific. You know, we waited 15 minutes to start the deployment, but the soil held together very well. The shot that Barry showed of the biobarrier, there was also no evidence whatsoever of dust on the deck of the lander either. So that was really good news for us. Can we go back to the solar array shot again? We'd gone through great lengths anticipating the worst, and being in a dust cloud and having the dust not settle. If you look at the center hub of the solar array there, we have a little umbrella, if you will. There's a piece of mylar over the top of it, and that was a dust shield in case it was still dusty even after we waited for the dust to settle, so the gears and the mechanism wouldn't run the risk of getting bound up during deployment. And then if you look at about the 5:30 position, you'll see there's two honeycomb panels there. The way the array starts, it's folded up against the side of the spacecraft. We light off a power wax actuator, and the preload kicks the array out on an arm, and then there's a piece of tape and a take-up spool that opens this thing up, and those two panels, it unfolds with the analogies like a Chinese fan. So when we saw the picture of the two panels together like that, and we saw the tension in the solar array, we knew that we had, they were open and latched. And that's really important because we are going to see some wind. And we've done all kinds of testing that they'll handle the wind as well. But we've got two solar arrays that are fully latched. When we got the Odyssey overflight, the first data that we had on battery state of charge was 101, 102% state of charge. The touchdown state that we had before Odyssey went over the horizon is that the state of charge had dropped it to 91% against a predicted 90% at touchdown, and then it was fully charged by the time we got back to talk to it again. So the spacecraft, it nailed it, and we couldn't be happier. And what we're going to do now is go through a few days of checking this thing out and turn it over to Peter. And Peter and all the instrument PIs can start doing their thing on the surface. Back to you, Veronica.
Yeah, you'll have to understand it's been an exciting day, and we'll get this right yet. There was one more major contributor, which all of us forgot to mention, and it was the entire European Space Agency, which kindly offered the use of the Mars Express spacecraft orbiter, and it was up there collecting the data, and luckily we didn't need a backup, but it was nice to have it because Odyssey and MRO performed well. So thank you also to the European Space Agency and Mars Express.
Okay, we're going to open it up to questions, and as usual, just please wait for a microphone to come to you. And I'm looking for my microphones. We'll start up here in the front, and then we'll start working our way back, okay? If we can bring a microphone up to the front, please. There we go.
Hi, Craig Cavalt with Aviation Week. Congratulations. One science question and one engineering question. Science for Peter. Your favorite polygon there, the area looks a bit scoured by the descent engines, and I'm wondering if you think maybe the ice, your surface hardness may indicate that ice may be quite near the top, since it looks like you blew away only about 1 inch, and then you get fairly hard stuff. For Ed, was there any wind today at all that the system could detect? And secondly, why do you think the chute deploy was a little late?
Well, you have a pretty good eye for seeing through the soil down to the ice. Those of us looking at the pictures up in the operations center weren't able to make that determination. I think it's hard to say whether the streaks you see in that picture come from the thrusters. We have to see all the way down closer to the lander to make sure that they really, originate at the lander. So I'm not ready to make the statements you made. I think all I could say is that we're very excited to dig into this soil and find out where that ice layer is, and I'm very hopeful that as we get the pictures of our digging area, we'll see one of those polygon troughs as well as the interior of a polygon, and we can do almost a cross-section across one of these things. Very important for polar research on the Earth, and I think probably the same for Mars.
Okay, regarding the parachute deployment, the parachute trigger, the primary trigger, works off of integrating the accelerometers in the IMU package. So when it integrates enough deceleration in the atmosphere, it tells the parachute it's time to deploy. So that took about 7 seconds later than we had planned, and there's a number of things that could account for that, either singularly or a combination of things. And what I'm going to do is I'm going to wait for the EDL team to start looking at the reconstruction without speculating. There's a couple of things that could drive it, but I'd rather talk to the team first. None that we've been able to detect. Not at the surface. Certainly when we looked at the weather leading up to it, there was a lot of evidence of dust swirling, but nothing at the surface.
Okay, go ahead and back.
Joe Palca from National Public Radio. Is there any indication, going back to the ice or the fact that you hope to see it, is there any concern seeing how little the surface was disturbed on landing that the robotic arm might have some trouble digging through this material? And second of all, is there any sense yet from the pictures that you've seen that you see anything like frost that might indicate some outcrop of ice?
Well, in the time that I personally have had to look at these images is probably a total of a few minutes. I would not say that I saw any frost. It may be very subtly found in some areas, but I haven't personally seen it. As far as the hardness of the soil, we have practiced in very, very hard soils, almost, a form of concrete, not full hardness, but partial hardness of concrete. And we can dig through those type of soils. That's the solid ice that we can't dig through that we expect to be underneath those soils. We actually did a field test some years ago in Death Valley where we used a similar arm to dig through the very hard soils that you couldn't have gotten a shovel into. And we just scraped away at it with our scrapers, and we were able to get down, I think, 10 or 15 centimeters. So this arm has a lot of capability for digging through hard soil, but not solid ice.
Henry Bortman with Astrobiology Magazine for Peter. How close is this terrain to what you expected, and what most surprises you about it from what you've seen so far?
Yeah, it's surprisingly close to what we expected, and that's what surprises me the most. I expected a bigger surprise. We see very few rocks, just as we expected, and we see the polygons and the trough depths. While I haven't measured them, they certainly aren't very deep, and just a few inches, I'm sure. And you could see them all the way out to the horizon, which verifies the fact that we don't need wheels on our lander. The one we're sitting on is just as good as the one we see on the horizon.
Okay, we have a question in the middle here. Just wait for a microphone to come your way.
This is Kelly Beatty from Sky and Telescope for Barry. What is the approximate coordinates of your landing spot? How far from the center of the ellipse is it? And full disclosure on any bets that were won or lost.
Well, no comment on the bets. I can give you the Latin launch. 234.3 is the estimated center of that 99% circle that you saw on the graphic we had a few moments ago, and the latitude is 68.2. Which is almost right on where we were predicting to land. Now, you asked how far from the center. I can't recall. I know the ellipse that you saw there was approximately 62 kilometers wide, so I'll guess that's about 25 to 28 kilometers. I see a nodding head by Gene. So that's about right, about 25 to 28 kilometers.
Anyone else want to answer the bets question?
Oh, no. I'm just glad that where is he? Oh, no. We had one person who bet on our infamous hill. Where's Eric Bailey? He's not here. All right. Yeah, he's one of the guys hoisting one for all of us.
Okay, we'll take another question then. Any more questions here? In the back. Bill, just wait for a microphone.
Thanks. Bill Harwood, CBS. For any of you, really, I was curious if you expect to be able to see the back shell, the heat shield, and/or the parachute, not from MRO but from Phoenix. And I know that in at least one picture I looked at, it looks like there's a white thing that some of us were fooled into thinking, is that the heat shield, is that the back shell, or is that an artifact or a defect in the image? Can you tell me about that? Thanks.
By the way, Ed thinks that it's a polar bear.
You've been running away too if you start blowing on him.
I'll take a crack at that. It's hard to say right now. Obviously, we've seen some images from various orientations around the lander, and we'll obviously within the next few days have full panorama and be able to see 360 degrees. The distance that the lander is from the parachute and from the heat shield is a function of a lot of parameters. Most notably, the wind is one. Frankly, the fact that we came down so well with so little horizontal velocity, it could be a combination of a couple of things. I would speculate that we had very low winds. We'll have to verify that through reconstruction. It could also be that we've nulled almost all the horizontal velocity out through the terminal descent phase. But the bottom line is it all depends on a number of parameters that our EDL reconstruction team will determine for us, and then we'll get a good fix on where to look.
Anything we can see in those images? Is there anything there of interest to you guys first cursory look?
Well, first of all, from Mars Reconnaissance Orbiter, it's hard to imagine that we'll be able to make out a lot of detail from that distance. Clearly, if it was close enough to Phoenix, obviously there's a lot of interest we can gain in that. When we had the luxury of going to look at the aeroshell and the heat shield on MER, we don't have that ability, obviously. But if it's close enough, we may see something. But
No, I'm sorry, I'm not trying to waste your time here, which we've already done at this point. There's a picture from the Phoenix that you can see near the horizon, something that's either an artifact of a defect in an image, or there's something there. That's what I was curious
We've all
about.
seen it, that's for sure.
But
It's
hard to say.
It didn't have a sign on it, so it was a little hard to tell what it was. But, this isn't our highest resolution picture. These pictures were compressed so that we could get them back for you today. And as we take higher resolution images, perhaps that'll come a little clearer, because I think there's probably several interpretations we could come up with out of this room right now. and I can see it in several people's faces. So let's wait a day. You know, we'd like to be able to have things to talk about tomorrow too.
Okay, we have a question over on this side.
Thanks. Todd Halverson of Florida Today. I was wondering if you had a pre-programmed script on board for the first couple of sols, or in fact 90 days, and if so, what is on the agenda for the next couple of days here?
Well, we had a pre-programmed script for today. For tomorrow, the team in Tucson is working very hard on that pre-programmed script, and in other words, it's not pre-programmed. And they will be setting that up on the Martian morning sometime late tonight. And depending on how we feel about our power situation and our communications abilities, how much data we can get back at the end of the day tomorrow, they will be adjusting the amount of things we can do. And since the power system looks so fantastically well done, and Ed's pictures just show that it went awesome, that I imagine they're going to cram a few extra things in. So I haven't actually found out what they're planning yet, but I will tonight, and we'll see what's on the agenda tomorrow.
Part of what we're going to have to do is finish a characterization phase with the lander itself. So we need a full diurnal cycle on the surface to see what the nighttime power requirements were for heaters, what the heater duty cycles were, how deeply we dug into the battery overnight, how quickly the solar arrays recharge the batteries in the day. So we need to gather all of that for a couple of days before we let Peter run wild on the surface, because we need to make sure that the science team has a realistic profile of how many watt hours of energy that they have as a function of the day, the cycle of the day, and then that gives them a whole lot better idea on how much that they can start trying to accomplish how quickly. So we need a couple of days really to make sure that we've done our engineering homework adequately.
Okay, no pressure, Peter, but what can we expect in terms of photos tomorrow?
We're going to try and take a panorama. I think it'll be in the opposite direction to the south. It won't be the full 360 because we won't be able to get it back in one day. But I believe it's around a third of a segment, 120 degrees. So it should be a considerable amount of data, and it probably will be in one color tomorrow, just so we can get a better sense of where we are. We're trying to fill in that huge panorama. So I hope we'll get that tomorrow evening, and I don't think we're having a press conference until Tuesday morning to show that to the public. But each individual image will be released as it comes down. The mosaics, we'll leave that to the hobbyists at home to put together until we can actually show ours. So there's a lot of people who really enjoy doing that, I understand.
Oh, yeah, we have a question on the phone.
Ray Jaffrey with Aerotech News up in Lancaster. First part, I guess, is for Ed. The press kit said something about maybe being able to go to 150 days or 150 sols until you reach a negative energy state. And the other question for Dr. Smith is if you can work longer, do you have enough crucibles and reactants on your mini chem lab, to make use of that productively?
I'll take the first part here. The primary mission is 90 sols. That's about 92 Earth days. And then we have an extended mission for another 60 sols. So that's how you get to the 150. So what will end up, there'll be evaluation that'll be going on through the summer to look at the energy balance, and we'll be plotting the amount of energy that we can generate, the amount of energy that's required to run the science, and we'll be plotting where the crossover point is on that for when we are no longer able to fully charge the batteries during a daytime cycle. And then we'll be trying to make projections on dust accumulation on the solar arrays that we factor into that. So we really need to see how we get through the summer and how much power we have, whether it's above or below the nominal predicts, and then we'll be figuring out at that point how long can we nurse the lander along after the primary mission. But the first order of business is to make sure that we focus the ability of the spacecraft to support the primary science.
Now, the question about how many samples we can analyze and whether we have enough crucibles to take advantage of an extended mission, we have the ability to analyze 22 samples. Now, each one takes several days, so then you have to gather that sample too. So that could be 70, 80 days of just analyzing samples that we gather, maybe even more. And that's not all we're doing. We have to do some digging, and we have to do some atmospheric studies, and we have a whole lot of other activities that we're going to be trying to pay attention to, and plus we have to account for some margin because we may have some down days. So by the time you add all that up, you're into already more than the 90 sols that we promised we would do, and you're into the extended mission. So I think we tried to balance the resources we brought with us with the amount of time and energy that we were able to use so that we didn't waste money by not using some of our resources or the alternative.
Steve, go ahead.
Any rough idea when the earliest you will begin the digging process? I know it's not going to be tomorrow or...
It's the end of characterization is when we really start the digging. That's probably at a week. If the arm is not too smart, we have to create a space for it to work in, and then we have to tell it where to go into that created workspace.
Okay, we have another question right over here.
Dave Perlman from the San Francisco Chronicle. I've got another question for you, Peter. When you said that the scoop might be unable to dig in the solid ice, is there a rasp-like tool in the bucket that
Yes.
could actually scrape away ice,
Yes.
some fragments of ice, to analyze?
That's exactly right. We don't claim to be able to dig down layer by layer through ice, but we can sample ice for sure. And we have a rasp in the back. It's actually the kind of tool used by ice carvers, ice sculptors, to make the fine details. So it'll cut the hardest ice. And it throws the chips into the back of the scoop, so you don't have to go around trying to pick them up off the ground. So
And what-
we've practiced this, and we know we can do it.
And what what happens to those fragments of ice? Will they go into the ovens to be baked
Yes,
and vaporized?
they go into the ovens to be baked, and if there's any organic material in it, it'll come out as a vapor that we analyze the vapor.
Okay, we have time for about 2 more questions. We'll start one back there, and then we'll take one more up at the front.
Hi, Andrea Thompson from Space.com and Space News. I was wondering if you guys officially start living on Mars time now that you're down.
Oh, it started, yes. Yeah, you're on Mars time now, too, so...
Okay, we'll take one last question here in the very front.
Henry Bortman again from Astrobiology Magazine. Peter, you've mentioned a couple of times this construction of the 3D space because the arm isn't so smart. Can you explain what that process is actually like?
Well, I've been cautioned not to say that the arm's not smart. It's a very smart arm. Just doesn't quite know where it is yet. It's very smart for an arm. It doesn't have any eyes yet.
Are you building this in the computer memory on the
Yes,
spacecraft?
we have the stereo vision we use, and that way we can measure distance, and we can make a 3D terrain, and then the arm knows where to go within that 3D terrain. It's all referenced together into the same reference frame. But before we do that, you're not quite sure how far away that surface is, and if you think it's one distance and it isn't, you can try and push it through the surface or scrape above the surface. You really have to kind of go stepwise to be sure you know exactly where the surface is with respect to the arm coordinates.
So when you say it's not smart, you mean it doesn't have any range finding capability?
Right.
Okay.
That's right.
Yeah, the arm, we call them teach points. You have to give it teach points. Right, so it knows where it's been. It's got an excellent memory, all right? But you have to tell it where it's been, then it remembers really well.
That's right.
Okay, that's going to be it for tonight's news briefing. Thank you so much for joining us. And tomorrow is a new Sol on Mars, so please do come back. We will hold a briefing at 2 p.m. Eastern Time tomorrow. and we will continue holding briefings daily, at least for the near future, at 2 p.m. Eastern Time. That lovely color panorama, you'll have to wait until Tuesday for that. But please do come back tomorrow for some more news. And in the meantime, you can follow us on the web at www.nasa.gov/Phoenix. Check there often, and we'll hopefully see you back tomorrow. Thanks for joining us.